everybody, it's Professor Mitchell. Today we are continuing with Chapter 8. We're going to talk about the student's t-distribution and how to use it to construct confidence intervals when the population standard deviation is unknown. All right, there's our disclaimer. Okay, so the objectives in this section are to determine the degrees of freedom to find and interpret the t-score of a normally distributed random variable, and then use the student's t-distribution to calculate the confidence interval for a population mean with an unknown standard deviation in business applications. So you'll recall that in the last video, we talked about how to find the confidence interval for a population mean with a known standard deviation using z-scores. All right, so this is pretty similar. The student's t-distribution is used whenever the sample standard deviation is used as a point estimate for sigma, which is the population standard deviation. If we draw a simple random sample of size n from a population that has an approximately normal distribution with mean mu and unknown population standard deviation, we can calculate the t-score using this formula. Notice that this is the same formula that we used when we were dealing with sampling distributions. One difference, when the population standard deviation was unknown, we used sigma here, and that was a z-score. So in the case where we're using S as an approximation for sigma, this gives us a different distribution. This follows a student's t-distribution with n-1 degrees of freedom, and we'll talk in a moment about what that means. The t-score, though, has the same interpretation as the z-score. It measures how far x bar is from the mean mu. For each sample size n, there is a different student's t-distribution. So a little bit about the degrees of freedom. The degrees of freedom in this case is n-1, where n is the size of the sample. That comes from the calculation of the sample standard deviation S. So if you think about how we calculate standard deviation, well, with one version of the formula, we find the mean of the sample, and then we subtract the mean from each value in the sample, and those are called deviations. So we use those deviations to calculate the sample standard deviation, but because those deviations add up to 0, we can find the last deviation once we know the others. The other n-1 deviations can change or vary freely. So we call this number n-1 the degrees of freedom, which is abbreviated df. So the notation for this student's t-distribution looks like this. T has the distribution of a student's t-distribution with, and then you substitute a number of degrees of freedom here. And that number is n-1, the size of the sample minus 1. So for example, if we have a sample size of 17 and we're using the student's t-distribution, we would say that the degrees of freedom is 16, and this distribution would be written like this. Student's t-distribution with 16 degrees of freedom. All right, so a couple of quick examples with finding degrees of freedom. That part is pretty easy. Researchers at a university have a sample size of 55, and they're using a student's t-distribution. What are the degrees of freedom, and how would the researchers notate this distribution? Well, since the sample size is 55, that means that this distribution would have 54 degrees of freedom, and the distribution would be notated like this. All right, here's one that you can try if you'd like to pause the video. It's pretty easy. You might have already done it. Statisticians conducting a census have a sample size of 24, and they are using a student's t-distribution. What are the degrees of freedom, and how would they notate this distribution? Well, of course, since the sample size is 24, that means we have 23 degrees of freedom, and we would notate it like this. Okay, so now for the interesting part. To write a confidence interval, remember a confidence interval is a range of values written with a point estimate and a margin of error. So just like in the last section, the confidence interval is going to have this form. You're going to start with your point estimate, subtract the margin of error, and then add the margin of error, and those would be the lower and upper limits of your interval. All right, so the point estimate is the sample statistic that is used to estimate population parameters. So when we're trying to estimate the population mean, the point estimate is the sample mean x bar. The margin of error is the error bound. So here is how you calculate the error bound in the case where the population standard deviation is unknown. When that population standard deviation is unknown, the error bound, EBM, is calculated with a t-score instead of a z-score. The error bound is found with the following formula, which looks very similar to the one we used in the last section. Remember, in the last section, the error bound was z sub alpha over 2 times sigma over the square root of n. So in this case, you're using a t-score instead of a z-score, and you're using s instead of sigma. T sub alpha over 2 is the t-score that corresponds with the confidence level alpha. S is the sample standard deviation, and n is the sample size. So using the sample mean as the point estimate and the EBM as the margin of error, the confidence interval at a confidence level alpha can be written like this. Now there are different ways to find these confidence intervals. You can use a graphing calculator to basically find the entire interval. I'll show that to you here in just a minute in case you are using a graphing calculator. I'm also going to show you a couple of other ways that I do it. So as an example, Dr. Lasso performs a study to determine how effective acupuncture is in relieving pain. He measures sensory rates for a random sample of 22 patients. Suppose the sensory rates are normally distributed with a sample mean of 8 and sample standard deviation 1.7. They want us to find a 99% confidence interval estimate for the population mean using the student's t-distribution. So what you see here is a portion of a table. This is a table that I believe we have not used before. I'm going to show you what the full table looks like, and I'm also going to put a link to the table in the description of this video. All right, so to find the confidence interval, you need the sample mean, x bar, and the error bound. So the problem gives us the sample mean, which is 8, and we're going to calculate the error bound with this formula. So we know the value for S, we know the value for N. We need to find the T value before we can calculate the error bound. So the T value is dependent on the degrees of freedom and the confidence level. The degrees of freedom is 1 less than the sample size, so we have 21 degrees of freedom. The confidence level is 99%, which means that alpha is 0.01. Remember that alpha is sort of the complement of the confidence level. And alpha over 2 is 0.005. So I am going to exit out of this for a second and show you what the table looks like. All right, so here's the table. We're going to go down to 21 degrees of freedom. And then at the top, you see that there are 2 different header rows. There's one that says area in 1 tail and also area in 2 tails. So if you're going by alpha over 2, that would be the area in 1 tail. So don't pay any attention here. That's just going to confuse everybody in that picture that they have that labeled alpha. Let's see. So the area in one tail, that would be alpha over 2. Okay. So we had figured out that for a 99% confidence interval, that means alpha is 0.01. So this here would be alpha, which means alpha over 2 is 0.005. So we're going to go by the first column of the table, go down to 21 degrees of freedom, and it gives me a t-score of 2.831. Let me go over also and show you, you can do this with technology. So I've gone ahead and loaded up a Google page where I have, move something out of the way here. I've typed T-distribution calculator into Google, and the very first result that comes up is my favorite website, StatTrek. So I'm going to click on that. All right, so the way this works, you need to fill in exactly 3 of these boxes, and then it will give you the value that goes in the other box. So in this case, we have 21 degrees of freedom. We're looking for a t-score, so I'm going to leave that blank. I'm going to go down here. It says the probability that t is less than or equal to little t. All right, so I think I should probably draw a picture here. Okay, so just to explain what I'm going to enter in that box. Oops, the funky looking thing. Okay, so in the middle we have 99%. And in the lower tail, we have 0.005. The t-score that I'm looking for is going to sit right here. Okay, so I want a t-score such that the area to the left of that t-score is 0.995. So I am going to enter 0.995 in that box. I hit calculate, and it gives me the same t-score that we got out of the table. For a problem like this, it's probably easiest to just use the table. However, when we get into hypothesis testing and finding p-values, you'll see I'm really going to be using this website a lot. And you can also use a graphing calculator to do the same thing that you use the website for. So going back to here, that explains how they came up with 2.831 for the t-value. So now we plug all the numbers into the formula. T is 2.831, S is 1.7, N is 22. You crunch those numbers, and you should try this on your calculator. Just make sure you know how to enter it. We get that the error bound is 1.026. So remember, the confidence interval is written X bar plus or minus the error bound. First do the minus, 8 minus 1.026, and then 8 plus 1.026. So the 99% confidence interval for this population mean would be from 6.974 up to 9.026. So the interpretation is that we estimate with 99% confidence that the true population mean sensory rate for all patients is between 6.974 and 9.026. I'll leave this up here for just a few seconds. If you're using a graphing calculator, feel free to pause the video and try this. Okay, here's another example. This is one that you could try if you'd like to pause the video. It should be pretty similar to the one we just did. The weight of baby chickens born at a certain farm are normally distributed with an unknown population mean and standard deviation. If a random sample of 21 baby chickens is taken and results in a sample mean of 12 ounces, that seems kind of big for a baby chicken, but anyway, and a sample standard deviation of 1.4 ounces, find a 95% confidence interval estimate for the population mean using the student's t-distribution. Okay, so again, here is the formula for the error bound. Using, so let's look at the table one more time. We have a sample size of 21, which means 20 degrees of freedom. And this is a 95% confidence interval, which means alpha is 0.05. So going over to the table, here is 20 degrees of freedom. Remember, this row here is alpha, so we could just go to the 0.05 column, go all the way down, and there is the t-score that I noticed on the slide, 2.086. Okay, so here we are. 2.086 for T. They gave us S was 1.4. They gave us N was 21. So this error bound comes out to 0.64, which means that the confidence interval is going to be 12 plus or minus 0.64, which gives me the interval from 11.36 to 12.64. So we estimate with 95% confidence that the true population mean weight for all chickens is between 11.36 and 12.64 ounces. All right, one last example. The amount of salt dissolved in a certain region of the Pacific Ocean is normally distributed with an unknown population mean and standard deviation. If a random sample of 23 gallons is given and results in a sample mean of 6 grams with a standard deviation of 3.4 grams, they want us to find a 99% confidence interval estimate for the population mean using students' t-distribution. I'm just going to say, don't count on the words students' t-distribution always being there. What's going to distinguish this kind of problem from the kind we did in the last section is whether or not the population standard deviation is given. The population mean will never be given. That's the whole point. We're trying to estimate it. But if the population standard deviation is given, then you do that the way we did it in the last section, just using the standard normal distribution and z-scores. You only use the t-distribution when the population standard deviation is unknown, which in real life is almost always. I mean, if you didn't know the population mean, why would you know the population standard deviation? Okay, so here's that formula again. One more time, I'm going to go over to table A3. The sample size is 23, which means the degrees of freedom is 22. And because we're looking for a 99% confidence interval, that means alpha is 0.01. So going back to the table, 22 degrees of freedom. And the area in two tails, which is alpha, is 0.01. So that's going to be this number right here, 2.819. Okay. All right, and then the sample standard deviation was given, and the sample size was given. You crunch those numbers, that comes out to 2.04 for the error bound. So the confidence interval is 6 plus or minus 2.04, which gives me an interval from 3.96 to 8.04. So with 99% confidence, we estimate that the true population mean weight for all salt dissolved in water I think it's salt per gallon in the Pacific Ocean is between 3.96 and 8.04 grams. And that's the end of this section.